Hello everybody, getting ready to do lesson chapter 7, review and summary, part 2 of pre-calculus math today. This will be a classwork lesson, so have your classwork sheet in front of you as we do this, and your note-taking guide as well, because there are 10 points here of note-taking, and there's 28 points that will go on your classwork sheet. Have that ready. If you don't have one, you need to get a hold of me for that. Students, put your name, date, period. If you're in my classroom, if you're a homeschooler, make sure you put your due date down here. Okay, and we'll start out today with a notebook entry here, students. What did you learn? So what did you learn? In 7.5, you learned add and subtract matrices and multiply matrices by scalars. And that is multiplying two matrices and use matrix operations to model and solve real-life problems. We did that in 7.5. And an example of that would be number 1, for let A equal A to the ij and B equal B to the ij be matrices of dimension m times n, and then let C be a scalar. So A plus B would be A to the ij plus B to the ij, and then C times A here would be C times the A. CAIJ would be how that would be symbolized there. And then 2, let A equal A to the ij be an m times n matrix, and B, let B equal B to the ij be an n times p matrix. The product AB is an m times p matrix given by AB will equal C to the ij, where C to the ij equals A to the I L, B to the 1, rather this would be A to the I1, B to the 1j plus A to the I2 times B to the 2j plus A to the I3, B to the 3j plus dot 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 A to the IN, B to the nj. Okay, so how about that for some abstract enumeration or symbolization there? How about that? Okay, let's go into an example of this. Operations with matrices. Find, if possible, A, B, and C, and D here. We got a 4-part question here for this situation here. Here's our A, B. So for A plus B is we're going to add these scalars together. So we just combine our different numbers here. They're in similar positions, and we come up with our sum over here of A plus B. And then our A minus B, now we subtract. So we go 2 minus a negative 3 would be 5. Negative 3 minus at 5 be negative 8, and then 6 minus a 5 here be 1, and then etc. down here. And then for C here, we have 2A would be 2 times this matrix up here, and this comes out to 4, negative 6, 12, 0, 8, and 2. Okay, part D of this solution is A plus 3B will equal, here's our A here, and then here's our B here, 3 times 3B. So when we add this and 3 times B, what do we get? We get negative 7, 12, 21, 3, 7, and 4. So 3 times this be negative 9, 15, 15, 3, 3, and 3. So let's see, negative 9 and 2 is negative 7. 15 and negative 3 is 12. 15 and 6 will be 21. 3 and 0 will be 3. 3 and 4 is 7. And then 3 and 1 will be 4. So that's how you get that. Okay, so page 5 here. What did you learn in 7.6 is the question. Use a formula to find inverses of 2 by 2 matrices, explanation and examples. So for 7.6, if A equals this matrix here and AD minus BC does not equal 0, then the inverse of A will equal 1 over AD minus BC multiplied by the matrix D, negative B, negative C, and A. So you just substitute from there into here, and then you create a fraction where your AD minus BC here in your denominator here. That would be the formula that you use to find the inverse of A. So putting that into practice here in these exercises, use the formula on page 536, which we just went over, to find the inverse of a 2 by 2 matrix. So we have a matrix here, and this is yours down here, students. So we'll do this one during our classwork here. And for this here, the inverse of A, we'll call this A. Here's our denominator, and then we come out here with our rearranged matrix here that we multiply by our denominator there, and we come out with this solution here once we do that. So this comes out to 1 over negative 40 times this, and then we come up with this as our solution. So that would be the inverse of this 2 by 2. What did you learn in 7.7? So find minors and cofactors of square matrices and find the determinants of square matrices. 7.7 explanation and examples. The determinant of a square matrix A, say of dimension 2 by 2 or greater, is the sum of the entries in any row or column of A multiplied by their respective cofactors. So, okay, knowing that, we'll go into our guided practice here, which we have find A, all minors. Our minors will go here, and then B will be our cofactors down there for this matrix here. So finding our minors here, this will be our minor 1, 1. Will be a 19, and then a minor of 1, 2 will be 6, negative 9, negative 4, and 2 will be negative 24. So 6 and 2, and then negative 4 and 9. So this gets blotted out, that gets blotted out, and then m of 1, 3 be 6, 5. So wait a minute here, 6, 5, and negative 4, 1. So it'll be 6 minus 20 would be 6 minus negative 20 be positive 26, etc. We did this in class. You did this on your homework. So we've all done that before. And they get these relevant sums here from doing that. And then we finish up over here. M33 would be an 83. 6, 5, so this would be a 40 minus an 18 be a 22, etc. So that would be our minors here. And then we just assign our signs. You remember that sign chart, students? By now you certainly know that sign chart. You just assign that to these different values here, and this is your final selection here of cofactors for this matrix. Okay, what did you learn for 7.8? Use determinants to find areas of triangles and to decide whether points are collinear. Use Cramer's rule to solve systems of linear equations, and use matrices to encode and decode messages. 7.8, our explanation and examples for 7.8. If a system of n linear equations and n variables has a coefficient matrix A with a non-zero determinant A, then the solution of the system is this. So x1 would be A1 over A, x2 A2 over A, and etc. here. So it'll be AN over A. where the ith column of A1 or AI is the column of constants in a system of equations, where the ith column is. It would be the constant column. So let's try one here. Solve the system of equations using Gaussian elimination, and B would be Cramer's rule. So this will be our Gaussian elimination here of this system here. Which method do you prefer and why? So I guess I'm going to let you do that one on your own, or do I do that for you? Well, let's see what I do. I do this one here. So we go from here. This is our start here. And see, we go down into here, 511. So we added something here. We got rid of our 2x there. So we multiplied. We must have multiplied this by 2. And then we added that to our central, or negative 2. Wait a minute, negative 2? Yeah, negative 2. Negative 2 times row 1. We added that to row 2. We end up with this. And then down here, x negative 3y. This stays the same, 7y minus 8z. And then this one down here, see, 66 over 7z. What do? We got rid of this. So we must have multiplied. We did something to get, this is a complicated maneuver here. From this stage to this stage, there are a few steps in between to get to this point. But the important thing here is we arrive at 66 over 7z equals 61 over 7. And then we come to 61 over 66 for z, and then we plug that in, then we solve for y, then we plug that into the remaining, and then we get to solve for x. So we get our ordered triple here by finding out what z is. And then for b, that's up to you students to solve that on your own. And that is, see, that's 12. 8 points here, students. I want you to finish that. Oh, I even throw that in. Goodness. Well, anyway, that's your Cramer rule here, students. You should be able to arrive at the same ordered triple by using Cramer's rule there as well. And that is your Chapter 7 Review and Summary, Part 2. And if you need classwork sheets, homework sheets, note-taking guides, etc., email me here, animatedpowerpointmathvideo@aol.com. Thank you very much.